Hi, good morning. I'm Oliver Gao. I'm the director of Cornell System Engineering Program. I have been very fortunate to conduct what I call the system conversations with our distinguished speakers that we invite to Cornell. Today, we are very excited and honored to have Professor Oli DeWeek with us. Professor DeWeek, he is Apollo Program Professor of Aeronautics and Engineering Systems at MIT. And he earned his degrees in industrial engineering from ETH Zurich, and then he moved on to get his PhD at MIT. His main research is system engineering with focus on how all the different complex systems, and also technology systems, and how should they be designed and even move on to be optimized across all the different fields. He actually, he previously served in a very important role for the development of system engineering. He was the editor-in-chief of the journal Systems Engineering from 2013 to 2015. I was editor before, and I know how it's really a service to the community, a growing community. And actually, he before that, he was a former senior vice president of technology, planning and road mapping. As you can see, these are all systems thinking, and he did that role at Airbus. You cannot believe, in that role, he was actually responsible for this road mapping of more than $1 billion research and development portfolio. I cannot help mention Oli's, aspiration and passion, which is to improve, our life on our home planet Earth, but in the meantime, keep our eyes wide open and pave the road for possible humanity's future on other planets, out of world living. So, Oli, it's really an honor and a pleasure to have you here. So, when I was doing the research, in preparation for this conversation, right, of course, I visited your website and I read some of your work. I saw that you did undergrad in industrial engineering, and then now you are really such important figure in systems engineering, which is taking shape. So would you mind sharing us, how your view and your mindset evolved through all these years that brought you, for example, from undergrad and then all the work here now, with this system engineering views and also thinking.
Very good. Well, first of all, I want to thank you for the invitation to come here to Cornell University. We share, I think, quite a bit in common. Definitely a passion for systems and system engineering. Yeah. But we also share a first name, Oliver, Olivier, very similar. Yeah. And so it's really great to be here, and it's an honor to speak to you. My interest in system engineering started pretty at a young age. I think I would say maybe I was, if you ask my mother, she would say when I was really little, she would tell me the story where I was playing in a sandbox. They had made a sandbox for me. It was a big one, and I was playing and everything. And I was playing, and then all of a sudden I stopped, and I looked at my mother, and I asked her, Mom, where does the sand come from? Because obviously the sand was brought in. It was in Switzerland. So where does the sand come from? As a little kid, and then they took me. It was a gravel, from the river basically. It was a few miles from our house, and then it was taken from the river and ground and brought by a truck. So I'm like, oh, okay, I get it now. And then she made a little booklet for me. My mom was an author. She actually made a little, drawings, and she gave that to me for my birthday, the story of where the sand came from.
That's beautiful.
But, so I've always been curious about where things are from, how are they flowing, is there technology involved in the middle, But it really started when I was doing my military service in Switzerland. So Switzerland has a mandatory system. It's a militia army. Mm-hmm. And so I wanted to be a pilot, a fighter pilot. Like many young kids want to be fighter pilots. Unfortunately, I didn't get very far because my eyesight, I basically failed the eye exam, and they said, no, you cannot be a fighter pilot. So I said, what's the next best thing? Well, maybe work on the airplanes, be a mechanic, fill up the fuel, repair the airplanes when they're broken after flight. So that's what I did. I became an airplane mechanic in the Swiss Air Force, a pretty young age, like 18. And the airplane I worked on was the F-5, which was done by Northrop at the time. And it's a pretty simple airplane. It's twin engine, mainly VFR only. It's a very basic airplane. But that was good because it was pretty easy to understand all of the different subsystems. So one of my favorite memories from that is a pilot comes back from the flight, and they have knee board. Something is wrong. So they write on paper, this is like in the late 80s, right, early 90s, and then they give you a ticket. Left engine, oil pressure low. And they give you the ticket and they walk away. And you're an 18-year-old kid with this ticket, and this airplane has to go up in the air in 4 hours again. Wow, okay, what do I do? Well, you study the problem. It's like solving a mystery, a crime. Why is the low pressure indication? What's the diagram of the oil pressure system? Is the pump failed? Is the filter clogged? Is it maybe a false indicator and there's actually no problem? So solving this kind of system problems at an early age in my military service gave me the taste for system engineering. And, I don't want to tell you there's a long story, but that was the beginning. That was the beginning of my quest and my curiosity to understand systems better.
That's wonderful, Ollie. Thank you for sharing those two stories. When you were a kid, you were asking, where the sand was from, and then this, airplane mechanic. I can see, from both those stories, I can see one very consistent thing. You want to look down the full chain, right? When you see something, even you start from this end. Either the left engine oil low, you start from this end, or you see the sand from this end, and then you dig down. You have this natural thing in your mind, right? You want to dig down, right, this full chain. I think that's such a nice, kind of, indication or representation of the system thinking, right? It's not like after me, I grew up at, I did my undergrad in civil engineering. It's pure engineer, right? It's not kind of systems, but you grew up with that, with you, in you.
Yes.
Yes.
And I will say another thing. I've lived half my life in Switzerland and half my life in the United States. And one of the things I really appreciated growing up in Switzerland was Switzerland has 4 official languages, national languages. So when you fill in your taxes in Switzerland, it's very small print because it's German, French, Italian, and a language that many of you have not heard about called Romansh. It's a very old language, comes from Roman times still. The point is, small country, 4 languages, living together in, I would say, relative harmony, and you hear all these different languages as a young person. And so you can't just say, okay, it's this way. Systems, what's really challenging and interesting about system engineering, system science is there are multiple viewpoints of the system. And to get a fuller picture, maybe we can never get a complete picture, but a fuller picture of a system, you got to take different viewpoints, like speaking different languages.
Yeah, I think, Ali, you're addressing really the root of, the system, not only thinking, but maybe, hopefully this could also be the root of even the system science. Right, it's really multifaceted, multi-perspective. Right, you look at things, and the result could be totally different. That's why as you mentioned earlier, before we formally start this, you mentioned that kind of 1 out of 7 engineers should be trained with system engineering. I think that makes sense because you can see the traditional engineers. Right, we are trained with. In mechanics, I think we have some overlap. For example, if you know the strength of material, we use sigma, right? The strength among material, and for engineers, you're given just one number. The strength is 175 psi or whatever, right? And then you use this number to do all those calculations, but it's kind of just one single line. Go down it, you derive the optimal. However, system engineer is right against that, right? There could be multiple perspectives, multiple solutions, and then probably in the end it could be a trade-off, right?
Absolutely, yeah. This is very interesting. One of the things talking about how we'll talk about education I think a little bit later, but one of the things that I think every kid learns or most kids learn in mathematics in probably high school or middle school is systems of linear equations, right?
That's right.
Do you remember Gaussian elimination?
Yes.
Or pivot tables. How do you word problems?
Yes.
So a word problem is something like this. Peter and Sonia are going to the orchard. Sonia has a big basket that can carry 30 apples. Peter has a small basket that could carry 12 peaches. Mm-hmm. In the orchard, they can get apples, peaches, and pears. Each of them can only carry 10 kilos maximum weight. Uh-huh. What is the optimal mix of fruit that they should get from the orchard? Something like this, right? You've heard this. Yeah. And you're like, it's written in natural language sentences, very much like, a requirements document from the government, for a new system.
Yes.
For doing maybe vaccine distribution or air traffic control.
Yes.
It's a word problem. Instead of being one paragraph, it's 1,000 pages.
Yes.
Right?
Yeah.
And then when we solve the word problem in middle school, we translate the human natural language into mathematics, right?
Yes.
And we have equations. And in some sense, we do a disservice, I think, to our middle schoolers, because the problem is always set up so there's n equations, there's n unknowns, and there's exactly one unique correct solution, for the system of linear equations. But in fact, real life is usually exactly not that case. Either there is zero solutions. Why? Because the problem is over-constraint.
That's right.
Right? So there is no solution to the equations, the constraints, the requirements. How do you deal with that? Well, you have to go back to your customer, your stakeholder, and renegotiate to come up with something feasible. Or the other situation that you get into, you have infinitely many solutions. Like you were saying, there's infinitely many solutions that could be satisfactory. How do you sample, find these solutions, and which one do you ultimately pick and recommend? So it's this is the world of system engineering, which goes beyond finding the one unique correct solution. Real life is not like this.
Absolutely, Ollie. I will refrain myself, asking you now, but I will come back to this later. But you made such a good point. It's kind of, you made, the disservice, to our children or students. I think we'll come back to that when we talk about education. But that's such an important point. So you mentioned, your right is the root of your systems engineering and systems thinking. Of course, then move on, and then you got more formal training and education, and then later on you yourself, right, become such important figure in this area. So now I would like to from this root, I want to hear how did you elevate from this internal kind of natural instinct of system thinking, and then get you to this academic and also scientific research career, and how through that career your view of system engineering, your understanding of system science evolved.
Okay. Yes. No. It's great, and it's really wonderful to think back and share that story, because it we all have our own unique path in life and our careers, and So the passion for things that fly, airplanes, satellites, I've had that for a long time. So I had a great opportunity in the early 90s. I was finishing up at ETH, and I got to be a liaison engineer on the Swiss F-18 program, which was the successor of the F-5. And this brought me to the United States, St. Louis, Missouri, which at the time was the headquarters of McDonnell Douglas, which is now part of Boeing. And so my job, I was kind of the youngest person on this team, and my goal was to be my task was to be a go-between between the American engineers and managers at McDonnell Douglas and the Swiss engineers and managers who were in charge of building a final assembly line, making modifications to the airplane. Some of these modifications actually were very simple. For example, the F-18 is a U.S. Navy airplane. And in the ejection seat, God forbid you have to eject from the airplane, there's a survival kit. In the survival kit of the F-18, you have different items. One of the items is shark repellent. Now, we don't need shark repellent in Switzerland, in the mountains. So remove the shark repellent. That's a very simple change that had virtually no knock-on effects on other parts of the system. You just remove that item, no problem. But there were some other changes we had to make that were much more complex. For example, when you're flying an airplane in the mountains, there's a lot of maneuvers, high G loads, instead of 7.5, 9G. Also, Switzerland tends to operate these systems for a long time, not just 15 years, but say 30 years. So the fatigue, you talked about mechanical properties of systems. Fatigue life,
yes,
very important. So we had to make a lot of changes to the airframe, reinforcements, substitution, instead of aluminum, use titanium, redesign. And what was really fascinating is, so we made bigger changes, but those changes did not stay local, like removing the shark repellent. They propagated. And that ended up being one of my research topics as I moved to MIT later, is how do we predict change propagation in complex systems? I have a system, it's already in place, but now I want the system to do something else. The mission is changing. Therefore, we're going to change things in the system, but those changes are not staying well behaved. They propagate like dominoes. You've seen the dominoes falling, but the dominoes can go all kinds of directions. So how do we really, ahead of time, predict change propagation in complex systems? That's one of my favorite research questions, and it was prompted by this experience at McDonnell Douglas. So I learned system engineering, or I was motivated by it in very practical context. And then the ability to abstract what's really going on to a higher level and ask more fundamental questions that may apply to completely different systems became really a driver of my interests and my research. Does that make sense? Yeah.
That makes perfect sense. Again, I think it's very consistent. It's kind of you observe something. Actually, that path, by the way, I think that path of going to a PhD study, I think it's much better than you do undergraduate. You continue on, right? Because you go to the program and you with all those real world application, the use cases, right, in your mind. I think that's that's very healthy. And also you mentioned this problem, right? Like in system architecting is really, of course, you are dealing with a legacy system.
Yes.
Right. You are looking at the propagation. Of course, now from system architecting point of view, imagine that if F-18 was built before. If they were designed beforehand with the potential Swiss modifications in mind, how would they, architect?
Absolutely.
That whole system. I
should say also that the Swiss were not necessarily we were difficult customers. I call it the watchmaker syndrome. This is, by the way, a Swiss watch.
The quality, the accuracy.
So one small gear in here is broken. The whole machine, the whole watch breaks down, right? So this sort of attention to detail and precision, it's kind of ingrained when you grow up there. So, but I think it's true in complex systems. You know, if this thing fails, is there another element is there redundancy in the system? Is there flexibility? So designing, like you said, a new system from scratch, we always use requirements or CONOPS, right? Concept of operation, use cases, who's the customer, what will they use the system for? And naturally, we have initially a bounded view of that, right? Yeah. If the system is successful, many systems are not successful, right? They don't actually meet even the initial set of requirements, and they basically are, they never get off the ground, or they're discontinued pretty quickly. But some systems are successful, and they operate for many decades, sometimes centuries or more. Yes. And the use cases will change. New requirements are coming, new customers are coming, new uses of the system emerge. And so we understand that now. So how do you design systems with the flexibility to be evolved and reconfigured is really also another interesting question. And that brings in things like modularity, real options, and so forth. Now, if the system is naturally flexible, you know, we can it has naturally the ability, even if you didn't think about it ahead of time, you can still make all these modifications. That's great. But if we can pre-think them more, that's even better.
Yeah, absolutely. Thank you for bringing our conversation to this next level. And as you were talking about, it's kind of, I think one key thing about system engineering is really life cycle, right? In comparison to traditional engineering, it's a snapshot of a life cycle of something. You design something. Most engineers, we just think about, okay, how do I design this new thing? But without thinking through, right? And when you talk about flexibility, maintainability, all those abilities, right? And of course, real options, how to whether it's worthwhile to build in the flexibility or not. I think that's wonderful. Now it's kind of with this kind of thinking, and I think one thing is that we as researchers, right, we all want to spend our life working on something we feel, changes the world for better. And of course, speaking of that, especially, when you try to identify the challenge, we want to address the key challenge. So what do you see as, some very important societal or either global or national or even local in different scales, but then there must be some consistency and commonality. But what do you see as some important challenge, especially system challenge, that you feel our generation or future generations will have to face and address?
Yes, so I think maybe I address the challenges of systems using the ilities, the life cycle properties. Maybe let's go with that one.
Yes, sure.
So I think the top ility that's perhaps the most important, at least from a human perspective, is safety. Yeah. It's basically whatever system we build, it shouldn't be harmful. I think that's definitely true in aviation. This is like safety certification, making sure that the failure modes of a system are, maybe we can't suppress the failure modes completely, but at least we can prevent harm, major harm to humans, to the environment. So safety to me is number one. And I think we've had several instances of systems that have failed in a spectacular way in recent years. But overall, I think the safety record of technological systems is getting much better. You definitely see it in aviation. Automotive industry, I think it's improving. It depends by the country. It's a big driver, self-driving cars. Yes. It's all driven by safety and failure modes, right? So that's a big one. The next one, I think we have to say very clearly, is sustainability, right? And it's essentially more than just environmental sustainability, but it's sustainability, the big S sustainability, economic sustainability, environmental sustainability. It's the ability of a system to really use resources, energy, material, very efficiently, so that we don't have to create so much waste in society. Waste, not just emissions, which is when people think climate change, it's all the CO2, right?
Yes.
It's a much bigger problem than this. It's plastics, it's water pollution, it's essentially with a growing world population, and the prediction is that we'll be about 10 billion people on this planet. That we just have to be much, much more sustainable. There's other challenges, but maybe I'll just leave it at those two: safety and sustainability.
Those two
top
are
two,
those top two are are wonderful. The reason I was asking about the challenge because I was going to follow up with my questions is kind of both challenges, safety and sustainability. Of course, sustainability is a much bigger, right? It goes even if you take safety, even an airplane, right? It's a complex system. Right, so in that sense, so for example, taking either safety or sustainability as examples, what roles do you expect system engineering to play in addressing those two challenges? And is our system engineering ready to address those challenges? And if not ready, how can we improve it?
That's a great question. So on system engineering, so on the safety side, I think and I want to give credit here to my colleague Nancy Levison. Professor Levison is a member of our lab at MIT, the Engineering Systems Lab, and she's been thinking about safety very deeply for many years. And what's clear is that the kind of failures that we're seeing in systems today are somewhat different than what we saw, 20, 50, 100 years ago. 100 years ago, you would have a boiler, in a steam engine or something. A boiler would explode, overpressurize or something, and cause a lot of damage. And that's primarily a mechanical failure.
Yes.
Right.
Yeah.
It's a component failure. Today, we can see failures in systems that are none of the components individually have failed. There's no broken shaft or boiler that blew up, and yet the system failed. Why? Probably either a combination of human, software. It's a dysfunctional interaction of components. And so there are new frameworks for thinking through safety accidents that allow you to think about the system losing control, essentially. The violation of safety constraints in a control system sense, including for software-intensive systems.
Yes.
So that's an area where I think on the research side we've made a lot of progress. There are frameworks for doing that, but practice is far behind. So the challenge there is we need to keep doing the research in safety methods, certification methods.
Yeah.
Obviously, the most obvious case now is the self-driving cars we talked about. There is no globally accepted certification regime for self-driving, highly autonomous vehicles today. But there are research methods and there are frameworks that can get us there. But the state of practice is really behind. So closing the gap between what the leading edge is in research and methods and what people typically do, either in the government or in industrial practice, that gap needs to be closed.
What are the barriers to close that gap?
Well, part of it is inertia, complacency, trust. There's a generational challenge as well, which I think is that I'm quite optimistic about this new generation that's coming up. Why? Because they grew up with software. They grew up with complex information-intensive systems, and they're open to new methods. And so the barriers are also economic. It seems to be it's expensive to run experiments, to guarantee safety and certification in systems that are what is a complex system? It's a system that can exist in many different states, right? The state space of that system is very large. So you have to really look at many different combinations of things that can happen, and that's expensive.
That's true.
Right?
And also, yeah, I totally agree with you. And also, Ali, you mentioned earlier, Nancy's work, and it feels to me, and it makes perfect sense to me that you can see, you use example of boiler, right? Human beings, we are already very good at dealing with all this mechanical, right? Either mechanical systems or mechanical components. We are, this kind of concrete, tangible things. But now today's, systems, and I feel actually the functioning of today's systems, somehow, those mechanical parts becomes the default. They are 100% reliable, but the major thing of this either software or human system interfaces this part. And you mentioned the future generation, and I feel it's really, the early generations and even our generation, I don't know if we are very well positioned to address those challenges, because somehow I feel out of the mechanical system, a well-functioning system today, there are probably, there is this expanded, either cyber or, these elements, which cloud-based computing, edge computing, I think our generation needs to learn. Lifelong learning. Learn new programming languages. Learn how to operate on the cloud. And learn how to... You can never stop learning in system engineering because technologies are moving fast. That's right.
Allow me to just say a word about sustainability methods.
Yes.
So one method that we have worked on for some years in my lab, it's called Generalized Multi-Commodity Network Flow. Mm-hmm. Sorry, it's a bit a long word, but the basic idea is that we can model, simulate, but also with data, represent the flow of resources through systems. The resources could be physical, information, energy, and as these resources flow through our systems, they get stored, they get transformed. Sometimes we have losses along the way, right? Contamination, and all kinds of things happen. But network and graph theory and flow theory is a very powerful method for modeling existing systems, but also future ones, and understanding, there's a bottleneck here. If we remove this bottleneck, then we could make a large improvement. There'll be another bottleneck eventually, but it's going to be somewhere else. Mm-hmm. So these network flow, modeling and simulation is very, very powerful now. Many methods, network flow modeling, discrete event simulation, agent-based modeling, extremely powerful methods, but they need to be validated using real-world data.
Yes. Ali, thank you for bringing that up. And I, of course, in the introduction, I did not mention that, but I think, in terms of, the methodological contributions, and I saw your group has been doing great work in this, time-expanded network, right? And also related to that, you just mentioned this GMCNF, this generalized multi-commodity network flows. And I'm now teaching, the system architecture course that Danny Stoll was teaching here when he was here. Mm-hmm. And I do agree with it's kind of how do we translate this real world system complexity into, for example, like graph theory, network theory, flow theory, such that we have a weaponry reservoir we can turn to, right, to address that. But offering that part in the translation, it's often one of the weakest point of our education. Yep. Right? It's really because, as you said, students are already given the translated problem, but they don't know how to do the translation. So when you talk about this, actually, this naturally gets us to the research. You mentioned that there is a gap between the research and the practice, but even on the research side, system engineering is yet to establish itself, as strong as other traditional disciplinary areas. So you and I, we talked briefly about the possibility of even system science. So where do you see, what's your vision about the pillar areas where you feel system engineering can evolve itself to maturity?
Yeah. So I think, and I hope there's not a lot of controversy around the fact that system engineering is a field of practice. I mean, we see,
It's engineering.
It's engineering, and there's a subset of engineers. And my theory or my suggestion is about 1 in 7 engineers should be a system engineer who's responsible for interfaces, how things work together, right, as a set, as a whole system. And then we can talk about why 1 in 7. But so it's a field of practice, but without a very strong theoretical foundation at this point. Right? We build a lot of systems, right? Medical systems, the air transportation, water supply, electrical, the electrical high voltage distribution network, high-speed rail. I mean, a lot of these systems, we are building them, we're operating them, we're evolving them, but the fundamental theory under this, I'm not talking about physics, chemistry, biology, but systems theory is pretty young and not very evolved, or at least not very accepted yet. And there's still a lot of competing ideas. It's kind of messy.
True. I agree with you.
Now, is that unusual for a new field? And I would say no. And so, I love to think about the future. You mentioned that. But I also like history. So I'll give you a couple of examples of other fields where I think we would say that's definitely a very respected, recognized field of science, of research, not just practice. One is architecture. Building architecture, building bridges, roads, buildings. If you go back to the Middle Ages, there were heuristics, rules of thumb. The arch, the supporting arch.
Yes.
How do you build like a dome? The Italians in the Renaissance, the dome of the Duomo in Florence. It's a masterpiece. It's incredible what they were able to build. But they didn't have finite element analysis, right? It was very, very basic understanding and a lot of rules of thumb, right? And then things did collapse sometimes, right? And they say, oh, we pushed it too far, so we should go back. But over the years, we start understanding free body diagrams, equilibrium, the material properties of different materials that are to be used in a building. And now, it's a science, right? Another example is thermodynamics. The history of thermodynamics, people like Boltzmann, for example, or Carnot, is fascinating. We have the first law of thermodynamics, the second law, and just those two, the first and second law of thermodynamics, took 150 years to be accepted worldwide with a common, understanding, a kind of consistent nomenclature. What are these variables? Internal energy, heat, entropy, enthalpy, the Carnot cycle. That did not happen overnight. It took 150 years for the theory of thermodynamics to be well established. But once it was, in some sense, the debate was over. It was a field, it was well respected, and it was foundational, and it still is foundational. So what we need in system engineering is essentially the equivalent of the first and second law of thermodynamics, but applied to systems.
That's Ali, thank you. That's such a nice historic perspective, and I think that will actually get people a very good, I think, context to think and understand the development of system engineering, right? Some people could be say, oh, actually, as you said, there is no theoretical foundation. But you look at how long those existing disciplines, it took those disciplines to develop a theory to support, right, a whole discipline. And you mentioned this. So, do you feel that? Would you like to point to some directions for the possible system theory? Of course, we're talking about future. It could come up, from one of those directions you point out today,
Yeah.
or it could be some other. But would you like to give it a try?
Yeah.
To point some directions? Yes.
Well, I think if you look at most, in mechanics, in even like in electrical engineering, in thermodynamics, the first law is always a conservation law, right? So there's a conservation of mass, conservation of energy, conservation of momentum, right? We talk about that, and so before you can. So there's two things that are important in a conservation law. First of all, what is the boundary of the system? Like in mechanics or in fluid mechanics, we talk about control volume. What's the control volume?
Yes.
In our field, in system engineering, it's the equivalent of the system boundary. We always say you have to define the system boundary. What's in the system, what's outside of the system, and what are the interfaces that cross the system boundary? That's number one. Defining a system boundary clearly is surprisingly challenging.
Yeah.
And then the second question, which is the more tricky one, what's the conserved quantity? Because it's not mass, energy, information. It's not mass, energy, or momentum. So my sense is it's going to be related to information. And probably the complexity of the information, because if you think about what system engineers do, well, we interview stakeholders, we write requirements documents, we create software code, we do test procedures, right? So all of those things are information-based artifacts that describe a current or future system, how it behaves, how it's structured, what are its failure modes. All that is information, but it's structured information. And so, there's a theory, information theory is a thing, and I think we need to look there. But that information is produced by humans, by the human brain. So we also need to understand the limitations of the human brain to generate, process, modify, and deal with all this information. So we have cognitive limitations of our brains, as capable as they are. And then to make it even more interesting, system engineering is not a solitary profession. There are some professions that are very lonely in a sense. Let's say you're a painter. Like Monet.
Yes.
You have your canvas, you have nature, you have your paint, and you're an artist. It's basically a solitary profession. System engineering is a team sport. You have to deal with a lot of people and talk to them and generate these progress, in projects. So usually the information we're talking about, these informational artifacts, whether they're traditional documents or models, like in model-based system engineering, they're produced by teams of people that each have their own brain, their own cognition, and jointly create these artifacts that then are connected to each other and superimposed, right, to create descriptions of systems that we can use to build them, operate them. So somehow the complexity of that information is, my sense, is the conserved quantity. But how exactly we formalize that, I think it's still in flux.
Ali, I think that's beautiful. I think you talk about three things: boundary, information, brain. I think this kind of. Speak of this, I feel the challenge or the opportunity that system engineers are facing. It seems to be totally different from, the theoretical challenge back, centuries ago when people invented either thermodynamics theory or those kind of Newton's law, those theory. Because before all our all those existing established disciplines where you observe the physical world and even one human brain, where you're able to do that, you can come up with a theory and you make such important contribution, and the field kind of jumped and then moved up. But now you mentioned that these systems science system theory, it's really a team sport, right? Individual brain, even say we say, we have numerous, we have endless creativity, but it has a limit.
It has
individual.
a limit. Yes.
It has a limit of individual. I'm not sure it's kind of then if we have an agent-based model of these multi-brains, and what kind of interaction mechanism will enable these interactive multi-brains to tackle those three boundary information and the problem? And I don't know if theoretically can we prove that yes, there is mechanism in existence that will be able to tackle that problem, or we can even prove that no, there is no way.
It sounds like a great thesis topic. But I think if you look at the history of humanity, us as a species, what really has set us apart, I think, is our ability to collaborate and create things together that we couldn't do individually. Right? So the collaborative creation of information artifacts to then build new systems, new capabilities that transcend what an individual or even a small group can do, that really sets us apart as a species.
Yes.
And we're doing it. We're doing amazing things. We're sending probes to, every planet has now been visited in our solar system by a robotic probe. Mm-hmm. Right? We've landed on the moon with humans. We are working on curing cancer. It's a long, we create vaccines against viruses now in a few weeks or months, which took years before. Yeah. Right? We can travel halfway around the world in just a few hours. These are incredible things. But we've done them without a formal theory. Right?
That's right.
And so we start to see the limitations of how much further can we go without a more solid theory. That's the big question.
That's very interesting. Ali, you mentioned this, and I think naturally led me to now in the big data age. Right? It's kind of there has been debate versus like we have mechanistic models, which is basically a reflection of theory, right? Supporting all these mechanistic models. On the other hand, you have this real data, actually, the big amount of data, and at the end of the day, it's really the decision making. Either it's a planner, a designer, a polymaker. It's a decision making. Before, when we were lacking data, we relied a lot upon our mechanistic model. But now the data here, if you think of the data as real practice, right? It come to us. Actually, data and practice, they are. Before probably our theory and the model were ahead of practice and also data. Now it seems like practice from time to day, practice the data, they're going to be ahead of the model thanks to this computational, right? Power. Of course, I don't have an answer, but it's when you talk about that, I could not help thinking. Right, in the future, how do we even say, okay, now system engineering is as a field is established because now this theory is established. But would that be the defining moment of a field, or because systems and practice?
Yeah, I think it's a great 2 points. One is I think more deliberately managing the complexity of our systems. Using complexity as a design variable or as an objective or constraint, but doing it explicitly, I think is something that will be revolutionary for system engineering. Complexity, active complexity management. We have budgets for everything. We have financial budget, mass budget, power budget, computational budget, but rarely do we explicitly budget for complexity. And I think we need to. So that's number one.
Yes.
The other thing is, some people have predicted the singularity where human system engineers will be obsolete maybe 10, 15 years from now because computation is so good. So we don't need human system engineer anymore. will be obsoleted as a profession because of computers. I really don't believe that. And I think there's a couple of reasons. Number one, humans, the creativity that we have, the idea, coming up with unconventional new solutions that are not based on just combining old ideas, but really creating new things. We're very good at that. And I think even though there is some progress on computational creativity, but it's an open question whether computers can really be creative as humans can. But the other is that humans are actually, even though we're messy and there's a huge, we're not disciplined often, but we are pretty efficient, even as thinkers, And it's been shown that our brain consumes about 20 watts. Right, so when a human being is at rest, when you're sleeping, or if you're working out a lot, then you could go, 200 watts or so. But if you're kind of at rest, your body consumes about 70, 80 watts. About a fourth of that energy is burned in our brain. But if you take the number of computations we can do, divide that by how much power or energy we consume, we are 3 orders of magnitude more efficient than even the biggest supercomputer in the world today. And then we do it together as teams, right? Yes. So there's something that is, at least I think in the next few centuries for sure, I don't see us becoming obsolete. And that gives me hope.
I absolutely agree with you. And it's really, the human creativity. And I think human creativity is a stochastic, random process. But computers, no matter how you do that, it's a deterministic.
Yeah.
Right. It's a, I think that's a very fundamental difference. So I think Ali, you mentioned earlier, now I think 2 things. 1, human brain, we do have endless creativity, and 2, human society, we are collaborative. So you and I, we are both in education, higher education system. Of course, we realize the key advantage of humans is that we have better brain, we can collaborate. And then, so how can we educate? And actually, not educate. How can we help our future generations to better take advantage of these 2 very fundamental, features that we enjoy?
So I think systems thinking should be already taught in kindergarten. That's a pretty radical statement. But I mentioned my question. Where does the sand come from?
That's right.
Most children, maybe not all, but most children, I think, have a natural curiosity. Because I think as our brain develops when we're really young, the synapses and our neural networks haven't fully formed yet in our brain, and so we're trying to make sense of our environment. We're learning new languages, new concepts. So maybe by age 10 or 12, a lot of who we are and how we think is already baked. Now we can still learn, and we are learning a lot. But there's so much emphasis on, high school and college, and that's very important. But I think systems thinking, systems engineering, a form of systems thinking or system engineering could and should even be taught in kindergarten and elementary school. Take the kids to the local water plant. Show them where their drinking water is coming from. Maybe it's pumped from a lake, or it's an underground well, and the water is then pumped through this network. And then when they open up the faucet in their house, the water coming out of that faucet, if they've seen it once, they understand that there's like 10 steps before that water comes out of the faucet. And just through examples, right? And kids learn very well through examples, and adults too, by the way. So that's where it should start, and then it's a lifelong learning. One of the programs at MIT that I've had the good fortune to be affiliated with, which I think is I would call a sister program to your program at Cornell, is the SDM program, System Design and Management. The average age of students in SDM is 32 years old. Some of them are in their 50s. They've already had 1 or 2 careers, and they're still coming back to get a master's in system design and system engineering. And so that's what I think we need to do, is create a lifelong learning journey around systems thinking and system engineering, and give opportunities. Some will start and stay with it the whole way. Some will join later. Some will maybe drop out and do something else, and that's fine. But that's, I think, the big vision, is the big hope that I have, is we'll have a continuum of opportunities to learn about complex systems. And you know, we have pieces of that, but it's not coherent yet.
Ali, I think that's such a beautiful point. And I think it's really, because it's so far, when you and I talk about system engineering, we did not talk about, for example, Newton-Raphson's optimization method. We did not talk about, for example, kind of all those, say, differential equations. What you are talking about, it's really, when you talk about, this from kindergarten, and I thought, that reminded me of you grew up in a multilingual, right, context, right? So it's kind of, how can we get this system thinking into the blood, just naturally?
Yeah.
Right. I think that will probably be the best hope for us. For example, through all this, cumulative and joint effort, someday there's someone who can help us make the jump in that kind of theory, which we feel it's lacking today. But because if we don't have the generations and general people coming this way, getting ready to make that jump, there's no way we can kind of break through.
That's right.
The
next generation, well, and the next after that. I'm very hopeful. I really am.
Yeah. So this is wonderful. So I of course, my final question is, I just want to give a very quick kind of, because you are coming today to deliver, Ezra seminar talk. Actually, you're talking about blurring the boundary, integrating system of systems at the edge of Earth and space. This kind of get me to, kind of your passion. Please share with us your passion. Tell us about that.
Well, it's pretty simple. This is our only home, the Earth, and we need to take care of our home. We have not been taking good care of our home as we've grown so much, as a species. We haven't taken care of other species, biodiversity, getting, water, energy, food, everything we need to thrive. We've been pretty careless, I think, with our planet, despite new technologies coming in. And so I think system engineering can help a lot, transforming our civilization to become much more sustainable, so that we do have a long-term future on this planet. But at the same time, I think we also are a very curious species, and we've shown that, right? We've been sending probes. We have even probes like Voyager 1 and 2 that have left now officially the boundary of our solar system, the furthest man-made objects ever. They're still sending signals back to us. It was launched in the 70s. So I think humanity will establish a permanent footprint beyond the Earth. We already have, in a sense, the ISS, which is very close, but it's been operated continuously without gaps for the last 20, 25 years now. And so, going back to the moon, Mars obviously is a big destination, establishing a presence there. By the way, we don't use the word colony anymore, because the word colony comes with a lot of baggage. So we talk about human settlements. So establishing human settlements there will help us a lot understand how to close these cycles, how to be more efficient, how to survive in really extreme environments, and then bring that learning back to Earth to improve and shepherd our resources better than we have. So that's my big vision, is that we will take care of our home planet, explore other worlds and establish settlements, but then bring the learning back to the home planet so that we can really have a bright future.
That's wonderful. You mentioned that system engineering, hopefully with its development, can help us take better care of our own planet Earth. So of course we're talking about migrating to other outer world settlement places. So I hope that system engineering will be fortunate enough to have talent in the future such that the evolution of system engineering, that speed will be faster, and it will be established earlier before we migrate to Mars. Because otherwise we'll mess up another planet before we grow up.
Good point.
Right. Yeah. Oli, it was a great pleasure. It was so stimulating to me, when we had this conversation. Thank you very much.
Thank you, Oliver, and it's wonderful to be here at Cornell University.
Yes.